Welcome to this session on number-based questions. Questions based on numbers are one of the favorites of test setters because of the sheer number of variations possible. Number-based questions can be designed to test either the fundamentals or the advanced concepts. Just because of the large number of variations possible, it will not be feasible to discuss everything in one lecture. In this discussion, we shall deal with one section of the number-based questions which will give us a good return on the time invested. Here we shall focus on divisibility and factor-based questions. Let us first spend some time to understand the basic concepts before we look at questions from this set. Take the number 30. We all know that it is divisible by 3. Now, what exactly do we mean when we say 30 is divisible by 3? What we mean is that if we divide 30 by 3, the remainder is 0, or that 3 divides 30 exactly into a whole number. Similarly, we know that 30 is not divisible by 7. This is because if we divide 30 by 7, we do not get a whole number. We get a decimal value. Or if we say in another way, when we divide 30 by 7, we get a remainder 2 which is non-zero. By definition, a number n is said to be divisible by another number p if p divides n exactly into a whole number of parts. In that case, the remainder obtained will be 0. Remember that all multiples of a number will be divisible by that number. When numbers are small, checking for divisibility will not be an issue because they are either familiar to us or we can actually divide and see. But it becomes difficult and time-consuming when the numbers are large. In such cases, it will be helpful if you know the basic divisibility tests. A set of rules for testing divisibility of numbers is given. Go through the rules given. Go through the rules. 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 Those were some easy rules that can be remembered. Beyond 12 also, there are rules. But they are not easy to remember and we do not require them most of the time. Let us look at the process of division a bit more closely. If we divide a whole number with 3, There are three possible values that the remainder can take. The remainder will be 0 if the number is divisible by 3. The remainder can be 1 or the remainder can be 2. If we divide a whole number with 3, the maximum value of remainder will be 1 less than 3, that is 2. If we divide a whole number with 17, let us say, then the remainder can take a maximum value of 16. It can be any of the values 0, 1, 2, 3, etc. up to 16. If it is known that the remainder obtained on dividing a certain whole number by 15 is 6, then we can write the number in general form as 15k plus 6. Similarly, if it is known that the remainder obtained when a certain whole number is divided by 11 is 2, then the number can be written as 11k plus 2. If a number a divides another number n exactly without leaving any remainder, then a is called a factor of n. If we write n equals a into b, where n, a and b are numbers, that is, if we can write a number n as a product of two numbers a and b, then a and b are called factors of n. For example, 4 is a factor of 20 because 4 divides 20 exactly without leaving any remainder. 6 is not a factor of 20 because when we divide 20 by 6, we get a remainder of 2. A number may have many factors. For example, 1, 2, 3, 4, 6, 8, 12 and 24 are all factors of 24. A number which has only two factors, 1 and itself, is called a prime number. Examples are 2, 3, 5, 7, 11, 13, 17, etc. 2 is the smallest prime number. It is also the only even prime number. In order to find the factors of a number or to see whether a number is a prime number or not, we just need to check with numbers up to the square root of the number. This will be familiar to students who have written software programs, as it is a common exercise in programming for beginners. Let me explain with an example. Take the number 80. Let us try to find its factors. 80 can be written as 1 into 80. So 1 and 80 are factors of 80. Similarly, 80 can be written as 2 into 40, 4 into 20, 5 into 16, and 8 into 10. So the factors of 80 are 1 and 80, 2 and 40, 4 and 20, 5 and 16, and 8 and 10. Note that for each factor A, we are getting a corresponding pairing factor B such that A into B equals n. In this case, there is no need to check beyond 8 because the next number is 9, whose square is 81, a number larger than 80. And if that number was a factor, then the pairing factor would be less than the number, and we would have already encountered that pairing factor in our trials up to 8. For example, if we take 10, 10 into 8 is 80. So 10 is a factor of 80. But observe that we have already taken 10 into account when we took 80 as 8 into 10. So there is no need of checking for factors beyond the square root of the number. Since 80 is having more than 2 factors, it is not a prime number. It is called a composite number. A whole number can be expressed as a product of prime factors. A prime factor of a number is a factor which is a prime number. When we express 80 as 2 into 40 or 4 into 20, it is not an expression as a product of prime factors because 4 and 20 are not prime numbers. However, we can modify that and write 80 as 2 into 2 into 2 into 2 into 5 or 2 to the power of 4 into 5. Which is what we mean when we say expression as a product of prime factors, because 2 is prime and so is 5. The process of finding the prime factors of a number is called factorization. Here, what we do is to go on dividing the number with exactly divisible prime numbers starting with 2. The quotient obtained is also divided in the same manner till the quotient we end up is also a prime number. Let us understand the factorization method with the help of an example. We shall try to express 280 as a product of prime factors. First, we try to divide 280 with 2, the lowest of the prime numbers. 280 is divisible by 2. So we divide 280 by 2 as shown in the slide and write 140, the quotient, as shown. Next, we check whether this quotient 140 is divisible by 2 or not. Yes, it is. So we divide 140 by 2 and we get the quotient as 70. We do the same process with 70 and we get the quotient as 35. Then we try to do the same thing with 35. But 35 is not divisible by 2. So we try with the next prime number, which is 3. 35 is not divisible with 3 either. So we try with the next prime number, 5. 35 is divisible by 5, which gives a quotient 7. 7 is itself a prime number, and so we will not be able to divide further by any other prime number. So we end the process and note the prime numbers with which we could divide the number 280 and how many times each of the prime numbers had occurred. We could divide 280 with 2 3 times and once each with 5 and 7. So we express 280 as 2 to the power of 3 into 5 into 7. End of base theory. Now let us apply the learning. We shall do 5 questions in this session, each one building on our conceptual understanding. Look at the first question given in the slide. Is the number 81720354 or 8,17,20,354 divisible by 6? That is the question. As you would have seen in the divisibility rules, for a number to be divisible by 6, it has to be divisible by both 2 and 3. Is the number divisible by 2? Yes, it is. Since the number ends with a 4, it is an even number and all even numbers are divisible by 2. So the number is divisible by 2. Now let us check the divisibility with 3. The rule for divisibility by 3 says that if a number is divisible by 3, then the sum of its digits will also be divisible by 3. So in order to check the divisibility of a number by 3, it is sufficient to check whether the sum of the digits is divisible by 3 or not. Let us add the digits. 8 plus 1 plus 7 plus 2 plus 0 plus 3 plus 5 plus 4 gives us 30. Is 30 divisible by 3? Yes. So the number 81720354 is also divisible by 3. Since the number is divisible by both 2 and 3, it is divisible by 6. Try out the next question on your own. We saw earlier that a prime factor of a number is a factor which is a prime number. The question asks us to find prime factor that is present in 168 but not in 96. In order to find this out, we need to find the prime factors of both 168 and 96 and compare them. Let us do that. The slide shows the factorization and prime factors. We can see that 168 contains 2's, 3 and 7. 96 contains 2's and 3. So the prime factor that is present in 168 but not in 96 is 7. Look at this question. When a number is divided by 7, the remainder is 4. What will be the remainder when the square of the number is divided by 7? Let us call the number n. This number, when divided by 7, gave the remainder 4. Then, as we had seen earlier, we can express n as 7k plus 4. That is, a multiple of 7 plus 4. Square of the number would be 7k plus 4 whole square, which is 49k square plus 56k plus 16. We are asked to find the remainder when this number is divided by 7. 49k square plus 56k plus 16 can be rewritten as 49k square plus 56k plus 14 plus 2. Why did we write 16 as 14 plus 2? We did it because 14 is divisible by 7 and 2 is not. Now look at 49k square plus 56k plus 14 plus 2 carefully. Here the term 49k square is divisible by 7 because 49 is a multiple of 7. 56k is also divisible by 7 because 56 is a multiple of 7. Similarly, 14 is also divisible by 7 because 14 is 7 into 2. The only thing that is not divisible by 7 is 2. When we divide 2 by 7, the remainder obtained is 2 itself. So the remainder obtained when the square of the number is divided by 7 will be 2. Now refer the question Q4. We need to find out the values of P and Q such that the given number is divisible by both 9 and 11. Since options are given in the question, back substitution method, where we plug in the option values and check the divisibility conditions to validate the correct choice. Let us look at the back substitution method. What we do here is to plug in the option values to the unknowns. Let us start with option A. When we plug in the values given in option A, the number becomes 121264. It is said that the number is divisible by both 9 and 11. The divisibility condition for 9 is that the sum of digits should be divisible by 9. Let us add the digits. 1 plus 2 plus 1 plus 2 plus 6 plus 4. It adds up to 16. 16 is not divisible by 9, and so the number is also not divisible by 9. So option A is out. Similar is the case with option D because the sum remains the same in option D as well. This is because the numbers are 1 and 2 itself there. Only difference is that P becomes 2 and Q becomes 1. Now try option B. There, the number becomes 1, 2, 3, 2, 6, 4. Is 1, 2, 3, 2, 6, 4 divisible by 9? Check the sum of digits. Sum of digits is 18. And 18 is divisible by 9. So the number is also divisible by 9. So far so good. Now, if that has to be the answer, it should be divisible by 11 also. The divisibility rule for 11 says that the difference of the sum of digits in odd and even places of the number should be 0 or a multiple of 11. I'll repeat. The divisibility rule for 11 says that the difference of the sum of digits in odd and even places of the number should be 0 or a multiple of 11. Let us add the digits in the units place. It is 1 plus 3 plus 6, which is 10. Sum of digits in the even places is 2 plus 2 plus 4, which is 8. Difference between the two, 10 minus 8 or 2, which is neither 0 nor a multiple of 11. So the number is not divisible by 11. Hence, option B is not the correct choice. So naturally, option C should be the correct one. If we want to be sure, let us try option C as well. Option C is P equals 2 and Q equals 3. Then the number becomes 1, 2, 2, 3, 6, 4. It will be divisible by 9 as the sum of digits is 18. Now test for divisibility by 11. Sum of odd digits is 1 plus 2 plus 6, which is 9. Sum of even digits will be 2 plus 3 plus 4, which is also 9. Difference of the two, 9 minus 9 or 0. So as per the divisibility rule for 11, the number will be divisible by 11. Hence, option C is the answer. Now look at the last question of this discussion, question Q5. Work that out on your own. When a number is divided by 11, the remainder is 5. When the same number is divided by 19, the remainder is 14. We need to find the lowest whole number satisfying these conditions. Hope you have given it a try. Let us look at this step by step. Any number that leaves a remainder of 5 when divided by 11 can be expressed as n equals 11p plus 5. The same number when divided by 19 leaves a remainder of 14. So it can be expressed as n equals 19q plus 14 also. Here p and q are whole numbers. Now since both the expressions represent the same number, we can equate the two. Therefore, 11p plus 5 equals 19q plus 14. From that, we can write p equals 19q plus 9 whole divided by 11. Now plug in the different values 0, 1, 2, 3, etc. for q. till such time that we get a whole number for the value of p. When q equals 0, 1 or 2, we get a fractional value for p. When q equals 3, we have p equals 66 by 11 or 6, a whole number. So the value of q is 3 and the value of p is 6. So the number 11p plus 5 will be 11 into 6 plus 5 or 71. That is, 71 will be the lowest whole number satisfying the given conditions. As far as questions based on numbers are concerned, what we have seen here is only a small set of possible questions. The important thing while looking at this set is that there should be complete clarity of thought on what you are doing. All the best. Thank you.